Yes, hello guys. My name is Frankie Lowino, and I want to talk about and look at malaria. Malaria, for most Americans who may not be aware, or people in the developing world, actually, in the developed world, malaria is a mosquito-borne disease, and this the Anopheles female mosquito actually is the one that carries this parasite that is known as Plasmodium falciparum. That parasite can lead to cerebral malaria, and normally the signs are vomiting and diarrhea and high temperatures and body aches, and just is a mess. I had it before in Kenya, and I had cerebral malaria, which put me down, and it affected me for quite some time even after that. So in the developing world, this is common, especially in places where we have stagnant water. It's generally bred by mosquitoes. And the anti-malarial drugs, there has been resistance to anti-malarial drugs over the years. And we are going to run malaria parasite clearance rate regression for a Bayesian hierarchical regression, and also using the SOM model. Now, we want to investigate how covariates can impact malaria using the recently developed BCE, Bayesian Clearance Estimator, which leads to more accurate results for hierarchical regression modeling. Now, the R package that was developed for this particular purpose is known as BHRCR, and it performs Bayesian hierarchical regression to estimate malaria parasite clearance rates along with the effect of covariates on them in the presence of the lag and tail phases. Now, all posterior inferences are obtained by a Markov chain Monte Carlo MCMC based on sampling scheme which forms the core of the package. Now, MCMC algorithms generally generate a Markov chain of samples, each of which will be correlated with nearby samples. Thus, if uncorrelated samples are required for inference, one can thin the resulting chain after the burn-in period by only taking every nth value, which is really what is called thinning. So I downloaded the library BHCRH, and the main function of this is to return the worldwide anti-malarial resistance network principal component estimates. That's what it stands for, WWARN, as well as the estimate from the Bayesian hierarchical model. Now, we will also download, of course, call in the library kernel, which we're going to need to do the SOM model. So the data postset, which I downloaded already, it's already inherent in the package BHCHR, and the dimensions of this, when I downloaded it, did it here already, so you can see it's 1,504 observations with 3 variables, and the 3 variables are the ID, time, and the count. Now, this data consists of Plasmodium clearance, Plasmodium falciparum clearance profiles of 110 patients, along with their individual level covariates, which were measured between 2009 and 2010 in the Pursat province of Western Cambodia, hence the name of the data known as the Pursat data. The parasite densities were measured every 6 hours, and the parasites were divided into 2 genetically different groups, labeled 1 and group 2. And all the 110 individuals were observed until no parasites were detected in their blood. That is the purpose of that. Now, we get the data posterior and plot the posterior, and why we need this and the Pursat covariate is that covariate is a data frame with no missing values, ordered according to patients' order in data containing individual level covariates. And the covariates in analysis, whenever you're doing random clinical trials, they can increase the statistical power and improve the precision of the treatment effect. Now, coming to the CEB function, the clearance estimator bias function is the principal function in the BHRC package that analyzes the input data in the Bayesian framework. Now, this part here, I'll highlight it. I have already run it, and the reason I ran it because it takes a long time, and I've only 15 minutes to do this recording, so I ran it in advance. And this is the function itself here, okay? This is the function, and we want to test the hypothesis that red blood cell polymorphisms, including hemoglobin and thalassemia, ethyl, and G6PD deficiency, may act to strengthen the pro-oxidant activity of the parasite defenses against artemisinin, which are the drugs that were used in this particular case, the anti-malarial drugs, hence resulting in lower clearance rates. And when I ran a summary of the results, the summary of the results is good here because it shows me there is no missing data, which is critical. So once I ran this algorithm here, and this part here leads to this, what we see here. You see, it tells us progress starts, and it may take a while. And it took a while, really. And it calculates the PC estimates, it conducts the Bayesian analysis, and you can see it does 50 iterations at a time. Now, let me explain this algorithm briefly. This algorithm, if you look at it, the data is allowed to have another predicted column, WWAR and PCE, which will be stored in another column known as predicted. Now, the detect limit is the detection limit of the parasite density in the blood, parasites per microliter of blood. And the default value is 40, but you see I took only 15. The burning is the length of the burn-in period. The default value is 500, but hey, I only took what? Took 50, because it's going to take forever here. The iteration is the number of simulations after the burn-in period. The default value is 100,000. We don't have 2 days here. We have only 15 minutes. So I took only 100. And the thinning is the size of the thinning process. The default value is 50, but I took only 10. So you can see that's what I ran. And the summary function which I did here, I ran the summary of the results, and this is what we come up with. See? And the summary allows us to perform an analysis of the covariates of interest. And one point of interest was whether or not there's evidence of resistance to artemisinin over time. That's the indicator variable here, 2020 true, for the year the data collection was included. According to the results produced, the parasite half-life increased over time because you have a positive mean and median. However, this effect is not significant because 95% of the credible intervals all contain what? 0. And you can see here, this is a summary of the result. You can see this at the confidence interval from 95% confidence intervals here, all containing 0. And these are the variables here. So including the year 2020 true, when it was measured. So I come here, you can see the posterior estimates, same thing, giving us the covariate of the log half-lives. And the half-life, as we know, is the amount of time it takes for half of the parasites to clear from the system. Now, the detect limit is here, so we are done with that. So I'll do the diagnosis of the results. I ran this, run that selected line, and the diagnosis and the plots are all stored and saved under MC diagnostics. So I'm not worried about that. So here now, from the results of the summary, I think none of these factors was significant and having a positive impact on the log half-lives, since the 95% intervals contain 0, as we said. So now I'm going to look at this and see, I can look at any individual in this data set. So I took individual 2, 4, 15, and 33 just to see what is the mean, median, and 95% credible intervals of each individual. This is possible. So when I run this here, there we go. You can see they had this individual 2, 4, 15, 13 had clearance rate of 0.13, 0.25, 0.12, 0.14, and this one's clearance median time was 0.13, 0.25, 0.12, 0.147, not much difference. Now, is this a time for me to create the SOM model? So the SOM model needs us to scale the data, in order to standardize the variables. So once I run this, scale the purusite data, There we are. So that is scaled. So I'm going to look at the sample size, and I'm going to at the same time take 75% of the number of rows. Okay, so you can see the data side I have 11,128. So then I take a random sample of all the rows here. Okay, so I have a random sample stored in a variable known as, an object known as train indices. Then I'm gonna, from that train indices, I'm gonna create my test and train data sets here. So I run that. So good. So now setting the seed is one important thing so that you can reproduce the results. I've set the seed. And to create the sum grid, we generally have to specify the size of the training grid prior to training the sum. So I'm running sum grid. I'm going to run the hexagonal shapes. So there we are. I've run that. Then I'm going to train my model here. So run that. Bam. Takes just a little while to be there. This is quicker. There we go. Voila, good. So now I'm going to do my visualization here. So let's look at this plot here and see how this works. So there we are. You can see a steady, you see, reduction in the mean distances between the nodes. So here I am. Then the cone and package, which I'd already downloaded, also allows us to visualize the count of how many samples are mapped, okay, in or to each node in the map. So I run this, and you can see the plot here. This shows me the node counts, which I don't have time to run into deep analysis of that, but you can see the node counts are here. Then I'm going to do this again using the neighborhood distance, which is sometimes called the U matrix. And it is a visualization that really helps us to look at the distance between each node and its neighbors. So I'm going to run that here. You can see, run that. There we are. You can see. So these are the clusters formed here. And that is with the neighborhood distances. So I'm going to have the node weights or vectors, which are made up of the normalized values. And that's how you do the normalization actually later, where earlier when we scale the data. Each node's weight is representative of the similar samples that are mapped to that node. And by visualizing the weight vectors across the map, we can be able to see the patterns in the distribution of the samples and the variables. So the weight vector view here, I can run this here, and you can see, here we are, okay? According to ID, time, and count, that's how they are clustered. This is the codes plot. Then I have to rush through this, unfortunately, because of time. Then I'm going to do a coordinate heat map creation. Coordinate heat maps are very, very important. So here we are. You can see they're put according to a relative clustering. So here I'm going to do the clustering and segmentation of the sum, okay, to isolate the groups of samples which have similar metrics. So this one I'm going to do here, and then plot it according to, these are the codes, there we are. Then I'm going to plot it according to the weighted sum of squares, and there we are, and it tells me the elbow is at 2. So it's telling me that 2 clusters will be ideal. So I'm going to run this with 2 clusters. I'm going to run hierarchical clustering here, create a sum cluster model there based on that, then plot it and see how it performs. Look at it. Let's check this. It's interesting. Ooh, okay, there we go. See, beautiful. Just formed it, demarcated it very well, okay, as I predicted here. So it has been organized into 2 well-defined clusters, as you can see, okay. So that's good for us there. Then I'm going to create hierarchical. Oh my God, I'm done. Okay. Okay. So